Imagine you're sitting in the living room reading a book, and suddenly you know someone is cooking bacon 2 rooms away. How does that physical information cross the house to reach you? Or think about a block of dry ice. You set it on a table, and over time it disappears into a thick fog. There is no puddle left behind. It goes straight from a solid chunk to thin air. Then there's the strange sensation of a spilled drop of nail polish remover. The moment that acetone hits your hand, your skin feels shockingly cold. We tend to trust our eyes. We look at a wooden desk, a steel bar, or a glass of water, and we see solid, unbroken material. We perceive reality as continuous blocks of matter, but our eyes hide the truth. If you zoom in close enough, none of that material is continuous. Every object you interact with is actually a collection of billions of separate microscopic particles, with empty space in between them. To understand how the bacon smell travels, why the ice vanishes, and why the acetone freezes your skin, we have to look at the 3 invisible rules governing these tiny fragments. This illustration shows water in a beaker, magnified millions of times. There are gaps between water particles. This is Rule 1. Particles have space between them. When dissolving salt, the overall water level doesn't rise because tiny salt particles slip into those empty pockets. Rule 2 is that these particles are never still. They vibrate, drift, and bounce. We call this movement kinetic energy. As you add heat to a substance, you give those particles more energy, making them move significantly faster. This explains how the bacon gets your attention. Heat from the stove supercharges the kinetic energy of the aroma particles. They bounce off one another, quickly diffusing across the room until they reach your nose. Rule 3 is attraction. This diagram shows people linking in different ways, from locking arms to touching fingertips. It demonstrates how particles pull on each other. Rigid solid particles hold tight, like the locked arms. Others just touch fingertips, making them easier to break apart. The amount of space, the speed of the motion, and the strength of the grip dictate the physical reality of every substance on Earth. This diagram shows the structural density of solids, liquids, and gases. These states represent different truces in a battle between energy and attraction. Solids are locked tight, liquids slip past each other, and gases have broken completely free. Whenever you put a pot on the kitchen stove, you introduce a weapon into this invisible battle. Heat fuels the particles' kinetic energy, giving them the power to vibrate violently against the attractive forces trying to hold them in place. The exact threshold where kinetic energy overpowers the force of attraction is what we call a melting or boiling point. This line graph tracks temperature over time as heat is added to ice. The temperature rises steadily, then stalls completely at the melting point. This is latent heat. The incoming energy is consumed to shatter physical bonds between particles, rather than making the substance hotter. This diagram shows a path called sublimation, explaining what happens to dry ice. Dry ice is frozen carbon dioxide. At room temperature, it absorbs so much latent heat that its particles bypass the liquid phase and jump straight to a gas. Melting and boiling are active environments where thermal energy physically dismantles a substance's structural bonds. You don't always need a rolling boil to break those bonds. Even below the boiling point, a few particles at the surface of a liquid gather enough kinetic energy to snap their connections and escape as a gas. This is evaporation. That escape requires fuel. To pull away from the liquid, those surface particles must absorb latent heat directly from their immediate surroundings. This explains the chilled sensation of nail polish remover. Acetone has very weak internal bonds, so it evaporates quickly at room temperature. As it sits on your hand, it rapidly absorbs thermal energy from your skin to fuel its phase change. As the highest energy particles escape into the air, they take that heat with them. The particles left behind have less total energy, which physically lowers the temperature of the surface. Your body uses this same mechanical trick when you sweat to stay cool. The reverse works just as neatly. When high-energy gas particles hit the side of a cold glass, they lose their kinetic energy on impact. They slow down, lock hands, and condense back into a liquid. Our environment looks like a collection of static, solid objects.